Welcome to the last part of section 6.2. We have a word problem here talking about a comet. Here's one really cool thing about ellipses. In space, if you have something like a sun and a comet, everything orbits in elliptical orbits. And what's cool is the sun, or whatever you're orbiting around, is right on one of the foci of the ellipse that's being made. So as you're orbiting around, what you're orbiting around actually sits at the foci of the ellipse, which is really cool. What's also really cool is that if you imagine every second this orbits as making a little triangle of area, so like from here to here, you can imagine this triangle is an area that it forms to the thing it's orbiting. That area is always constant, the area of this triangle, just like the two lines always add up to the same number. And so that's why things orbit much faster when they're closer to the star or the thing they're orbiting around, because in order for that area to remain constant, the triangle has to be bigger, it has to be wider to add up to the total area of the really long, skinny triangle. So this thing whips around, it slows down outside, slows down, then as it gets closer, it whips around again, and so on. So if you watch any videos, other videos on YouTube of comets and stuff, you'll see them whip around whatever it is they're orbiting around. Anyway, let's get to the problem. It says the comet C has an elliptical orbit of eccentricity 0.9676 with the sun at one focus. So let's draw a picture of that. Here's our ellipse. And now let's do our little sun right there. The greatest distance of the comet from the sun is 3797 million miles. Find the smallest or the least distance between the comet and the sun. Well, if we look at this, we see that here's our star, and where do you think on this ellipse is where we're the furthest away? Where are we the furthest away from the star? The furthest we're going to be is right here. Would you agree? Here's comet C. So here is the furthest distance we are away. And so the question is, what is that distance? What is that distance? And the answer is, that distance is equal to A. Because here's the center. That distance, this distance right here is A, if that's the furthest distance. But that's from the center. And we need to know this distance right here. That's the shortest distance. That's the distance we want to know. So how can we figure this out? Well, what this will be is, if we look at this right here, this distance, remember, is C, because that's the difference from the center to where the sun is, where the focus is. So that distance is C, this distance is A, and so how far away is the comet from the sun at the furthest amount? That distance is C plus A. So C plus A is equal to 3797, because C plus A is the furthest distance from the comet to the star, if that's the focus. All right, well, that's not helpful because it's a little helpful, but we need one more equation. They also told us eccentricity. And so remember, I gave you the formula for that up here. We don't know what B is, and so we can use this formula, though, C over A. So the eccentricity is, remember, it's E is equal to C over A, or 0.9676 equals C over A. So there you go. So now we have two equations and two variables, and now we can just solve. So what I would do is I'd multiply this equation on both sides by A, or 0.9676A equals C. Okay, 0.9676A equals C. And then just substitute this into the other equation, giving us, this is what C is equal to, so replace C with 0.9676A plus A equals 3797. Okay, so we replaced C with what it's equal to, which is 0.9676A. So remember, that's 1A, so we can add like terms. 1.9676A equals 3797. And then just divide both sides by 1.9676. Oops, actually that doesn't cancel. I shouldn't have crossed that out. Let's do, clear that, 3797 divided by 1.9676. So we get A is equal to 1929.762. Okay, so that's that distance from here to here. Let's find out what the C distance is. So C is equal to, again, we can just do C plus A equals 3797. So that means that, or actually, look, I've got it right here. C equals this number times A. It doesn't matter which equation you use to find out what C is. So let's do this number I have in my calculator, which is A, times 0.9676. And that will tell me C, which is 1867.239 if we round. Okay, so we've got A and C, which is very helpful. So what are we trying to find? We want to find the least distance between the comet and the sun. And that's going to be that distance right here. So what distance is that going to be? Well, remember, from here to here, this distance is also equal to A. So if we do A minus C, that'll tell us this remaining distance right there. So the answer is going to be A minus C. And we've got A and C right here. So let's do that. So it's going to be 1929.762 minus 1867.239 for an answer of 62.523. So approximately 62.523 million miles will be the shortest distance. And in fact, when NASA astronauts and engineers calculate this stuff, they remember to do it all with elliptical orbits. That's the orbits they have to match up to land probes on an asteroid or land something on the moon, or who knows, land something on Mars. So let's just really quickly go through the logic of that again. The longest distance was 3797 million miles, and that we found out was equal to C plus A. So we had that as our first equation, and then the elasticity equation is our second. With two equations and two variables, we were able to solve for A and C. The shortest distance, what we want, is the entire length A minus C. This distance right here is A minus C, and once we did that, we just got our answer. So hopefully you like ellipses. I think they're pretty cool. They're used a lot in space and astronomy, excuse me, and looking at the orbits of things out in space. So if this was helpful, please make sure you like and subscribe. If you have any questions, please leave them in the comments and I will answer them. I will see you in 6.3 to talk about hyperbolas. See you there.